Hey everyone, welcome back. In this video, we'll talk about how to extend and evaluate that multiple regression model. So let's get started. We'll start with evaluating a regression model based on residual plots. This will be very similar to the techniques that we use in simple linear regression with a single variable. We'll talk about how to evaluate how well our model describes the variability in the data and whether or not to use multiple R-squared versus adjusted R-squared. And then we'll also talk about how to add an interaction term to our model, what that represents, and when that might be useful. So let's start with the multiple regression assumptions. These are very similar to the basic linear regression assumptions. We're still looking to see that our linear model is a good fit for a relationship between a response variable and an explanatory variable. For that I assumption, we'd still like to see our observations be independent. That in turn leads to our residuals being independent. We'd also like to continue to see our residuals be normally distributed, and we would like that error variance to be constant. So let's take a look at an example for the residual plots from the PREVENT study. So in a previous video, we fit a multiple regression line using this data set. Here's what those residual plots look like. Now again, these are generated in R using the plot function, so creating a plot of our model. 4 plots are created, but we typically only want to look at the first 2. So with these first 2 residual plots, what can we see? Well, looking at the residual versus fitted line plot first on the upper left. Overall, it looks like there's no major trend in the residuals. That red, smoother line is pretty close to a horizontal line, about 0. There may be some concerns about increasing variance as the fitted values are increasing. This cloud of residuals is starting to widen. We're seeing more variation in the residuals. On the next plot, this normal QQ plot, this looks really good. This is about as good as you'll get with true data that's not simulated. We're seeing these points fall pretty close to a normal QQ line, indicating that the residuals for this model are in fact normally distributed. So that's a great thing for us to see. Now, we can also measure how well our data fits our model with a measure called R-squared. Now, in simple linear regression, we called this R-squared the coefficient of determination. And this measured for us the proportion of variability in the response variable y that can be explained using our linear model. Now, for multiple regression, we do have the same idea. What we'll do is calculate a value called multiple R-squared. Now, in this case, we'll find that by taking the correlation between the observed value y and the predicted value y hat and squaring that. Here we're using the predicted value to find the correlation because there are multiple explanatory variables, and we'd like to take those all into consideration at once. Now, because there are multiple variables, we run into kind of a conundrum, and the conundrum is this. No matter what, as we add a variable to our model, as we increase the number of variables that we are using, we're guaranteed to increase that R-squared. It will never go down by adding variables. So what that means is we might be adding variables to our model with very little gain in terms of explanatory value. So what we'd like to do is try to explain as much variability in our response variable y as possible while trying to keep a small model. So one metric that we've used to measure how much is actually being added is something called the adjusted R-squared. Now, this adjusted R-squared is a measure of the quality of a model that takes the multiple R-squared and shifts it downward. So here we're using P as a representation for the number of explanatory variables in our model. So as we increase this P, as P goes up, R-squared adjusted will go down. So we will shift it downward to essentially penalize for having too many variables in the model. Now, depending on your goal, you might choose to use multiple R-squared or you might choose to use adjusted R-squared. So as a basic rule of thumb, if you're trying to explain the variation in your data set, use the multiple R-squared. If you're trying to choose between one model or the other, I would recommend using adjusted R-squared because, again, that tries to adjust for the number of terms that are in your model. So let's take a look at this multiple regression model that's using age and statin use to predict the RFFT score. How much of the variation in active heart rate can be explained using this? Excuse me, active heart rate here is a typo, so please ignore that. That should be the figural fluency score. We're explaining about 28.5% of the variation. Notice that this adjusted R-squared has been brought down just a little bit because there are two variables in our model. Now let's take a look at interaction terms, and these can be incredibly helpful for us to expand our model because they allow the slope to change based on some factor. So if you want to directly measure how two explanatory variables are related, we might do that by introducing an interaction. So we say that an interaction exists between two variables if they are not independent. If the value that we observe with level A of one variable changes depending on what level another variable is at. If they change together, then we have an interaction. The way that we address this in a regression model is to add an interaction term. Most of the time, this interaction term looks like this. So our interaction term x sub 1, 2 is simply the product of x1 times x2. So let's add an interaction term to our model here with statins. So x1 is the age variable, x2 is the statin use variable. Remember, this is a binary variable that takes on a 1 if the user is on statins, a 0 if the user is not on statins. So now what we have is a model with 4 coefficients. We have 1 for the intercept, 1 for the slope on age, 1 for the slope on statin use, and then 1 for the slope on the interaction term, the product of age and statin use. So what does this really do to our model? Well, we'll explore this a little bit more in class during a lab activity. But the idea here is that including this interaction term will allow us to change the slope in our regression model based on whether or not we're using statins. So for example, here's what our fitted linear model looks like. Now, if we have a statin user, x2 is equal to 1. So we'll plug in a 1 here and here. Notice what happens. We end up combining two terms, this one and this one. We also end up combining two terms to create a slope on age. So notice that the slope on age for this statin user model ends up being different to the slope when we include a 0 or the not statin use category. So we're allowing with an interaction both the slope and intercept terms to change depending on some category. Now, what does this look like in practice? Well, here's an example of the overall fitted linear regression model without the interaction term in it. Contrast that to what happens when we add the interaction term into our model. I do want to point out here that what is changing to generate this is that inside that geom smooth function, which is what's adding the regression line, we are allowing the color of that line to change based on the level of statin use. That allows the underlying model and slope itself to change. So this incorporates the interaction term in the plot. So as you might notice, the slope on statin use, the blue color, is a little bit less steep than the slope on non-statin use. Now let's take a look at another example with an interaction term. So according to previous guidance that was issued, individuals with type 2 diabetes ages 40 to 75 with low LDL cholesterol between 70 to 189 milligrams should be on statins. For non-diabetic individuals, those individuals of age 40 to 75 with a predicted probability of future clogged arteries of at least 0.075 should be on statins. Notice here that the recommendation for whether or not an adult should be on statins changes depending on whether or not they have diabetes. Now, why is that? Perhaps there's an interaction here. So let's take a look at an example. Here we're augmenting this with data from the NHANES database, and here's what we're trying to look at. We're looking at the relationship between age on the x-axis and cholesterol on the y-axis. Is this relationship between age and cholesterol changing with diabetes? Well, let's add two regression lines. Let's add a line, or add a smooth line for diabetes yes in blue, diabetes no in coral orange pink. You can see that there is a pretty strong difference in the slopes according to these two groups. So when we see a difference in slopes, that tells us that this interaction term should be included. Whereas if the slopes had been similar, if the two lines hadn't really intersected, then we wouldn't need to add an intercept term if the slopes were very similar. So here this strongly suggests that we should include the interaction. And in fact, if we do fit a model to predict total cholesterol based on age, diabetes, and the interaction, this interaction term down here is in fact significant. We are gaining information from including that. So in the next set of videos, we will shift gear to our final class of data for the semester. We'll start looking at methods for analyzing categorical data. I'll see you then.